Good morning to everyone coming over or dialing in over from the East Coast of the United States, and good evening to the brave souls that are dialing in from Europe. Jack already introduced me, so I'm going to skip this, but today we're going to talk about standards. And before I go deeper into the particular use cases in biomedical imaging, I would like to talk a bit more broadly about what standards are. So, to begin with, standardy to nic innego jak forma języka. Standard to sposób komunikacji. Jeżeli nie znalibyśmy wspólnego języka, nie bylibyśmy w stanie się komunikować i wspólnie budować wielkich rzeczy. Well, if you haven't understood any of this, this is probably because we have not been using the same standard. Because if you look at it, language is a form of the standard, or in other words, a standard is a form of a language. It's all about communicating. It's all about finding the same level playing field to be able to exchange ideas. And when we are able to do that, we are able to build things together. It's basically the essence of collaboration. And languages, even though they usually evolve over hundreds of years, are a form of a standard. I subscribe to communicating with you using English, and only because of that you are able to do this, because you have also understood the rules of that language. And even though languages evolve over time, over, as I mentioned, ages or millennia, some of them actually have been designed de novo, from scratch, in other words. For example, Esperanto, which is an artificial language created in 1870, which was optimized for how easy it should be to pick it up and learn, which is just a neat example of how people introduce artificial standards in languages as well. But languages are not the only examples of standard out there. Probably each of you have a computer. And that computer has a plethora of different ports and connections you can plug into it. And this is another very common occurrence of standards. And those connections are industry acknowledged, approved way of communicating between hardware. And probably you recognize some of the ports in this picture. And this is how I can buy a piece of hardware, for example, a laptop, from one manufacturer, and then buy a microphone or a webcam from another manufacturer and plug one into another. And those two manufacturers, they do not have to work with each other directly. They just need to subscribe to the same language, to the same way of exchanging information via a hardware connection. And that's how all these different plugs and ports come along. And there are more examples, especially with the hardware industry, where standardization doesn't always go that well. For example, many of the laptops that are coming out right now have this new fancy port, sometimes referred to USB-C, sometimes referred to Thunderbolt 3, and this port looks exactly the same, even though it could actually provide many different functionalities that are not totally compatible. So that also shows that even in the industry hardware world, there is a need for standards that are clean as well as intuitive, both for users and the manufacturers. And we can go further. For example, the way we deliver electricity is another form of standardization that is very important. So for any of you who traveled a little bit outside of your country, you probably noticed that the sockets in the walls that deliver power have different shapes. And most of North America, it's a specific standard from NEMA, and most of Europe is also subscribing to a different standard. And of course, there's the UK that has to be different. But that's another way of benefiting from doing one thing the same way. Because if we didn't have a common way of delivering power to our appliances, each manufacturer of appliance would have to basically find some sort of a deal with a power provider or become the power provider itself, which is preposterous. And then we have digital communication. So in other words, the internet. And that's another example where agreeing on a common standard of communicating and encapsulating information in packets allows many services built by different companies that sometimes outright compete with each other to operate on the same layer and be able to communicate with each other. For example, both Bing and Google are using the same TCP/IP protocol to communicate with their customers and with each other, even though they're at outright competition. And then we also have a higher level of digital communication. The application programmatic interfaces, or APIs. This is the way how modern web applications can be built very rapidly, and you can go from a prototype to a scalable solution very quickly by using those standardized ways of scheduling services and receiving results from plethora of different things. Right now we have APIs for very sophisticated procedure, for example, detecting faces from pictures or detecting mood of a particular person from a recording of their voice. So this thing has been flourishing a lot. So you might ask how these standards are actually developed in the industry, how all these advantages of having a common language actually come about. So in the industry there are a few organizations that try to help different industry players to start talking with the same language. And one of them is the Institute of Electrical Electronics Engineers, the IEEE, in other words, which is known in some circles for publishing engineering content. But one of the big things they do is working on standards. So one of the standards that they're very famous for is Wi-Fi, or in other words, 802.11, which is an extension of the 802 standard, which is just Ethernet. And that standard allows different appliances to talk to each other wirelessly. And this standard was developed by IEEE by bringing different industry players into the same process. And IEEE has a process for deciding what should be in the final standards, and this process involves a draft that is then refined, that is then voted upon, and if it has enough votes, it basically becomes a standard. And IEEE is acknowledging the role of different players in the industry. So here, when it actually comes to voting, in many occasions, it's not people voting for a standard, but particular key industry players voting for what should be in the standard, what should not. Another example of a standardization body is the World Wide Web Consortium. So this one is very well known for higher level markup language that we use on the internet almost every day. So coming from the very commonly used HTML, which then became XHTML, through styling such as CSS and images like scalable vector graphics. All of these things were standards proposed and working by the World Wide Web Consortium. And right now they enable web developers to build websites and be relatively certain that those websites will work and be rendered in a similar way across different web browsers. And those who did web development know that actually adherence to those standards by different web browsers has been historically problematic, and quite often there are some rough edges that require developers to work around certain problems, in particular tools that do not implement those standards very well. And World Wide Web Consortium also has a process, and it also involves multiple drafts and release candidates that are either advanced to the next stage or refined. And this multiple levels of proposals is important because each time you elevate a particular proposal to a new level, that rings a lot of bells, and that promotes a lot of players to contribute time and look at the standard. And basically, it's basically a signal saying, hey, this will become a standard soon. You should have a look at it now before it's too late to make any changes. And then finally, something much more relevant to biomedical engineering, there is the National Electrical Manufacturers Association, or NEMA, which is not only famous for standardizing the electrical plugs in the US, but also for the DICOM standard, so Digital Imaging and Communications in Medicine standard, which is widely used in clinical applications for storing and transferring medical imaging data. Has been used for quite a while. I think history reaches the 80s, and it has seen a lot of revisions, but it is widely adopted in different hospital settings, even though adherence to this standard is sometimes not perfect, especially when it comes to neuroimaging, and even more when it comes to cutting-edge research neuroimaging. But that's the industry. And I want to talk a little bit more about standards in context of research or in context of academia. So here the situation is slightly different, and I would like to explain where those differences coming from. But before we actually go into the cultural changes, I would like to point you to this fantastic resource, this website called fairsharing.org, which allows you to search across different research or academic standards that are out there. So if you are if you would like to, for certain products, procedures, or databases, you would like to adhere to a standard and basically see what how other people try to solve the problem you're struggling with, this might be a great point to start, basically looking for standards that are already developed in a particular field that you're interested in. Okay, so let's talk a little bit how different standards in academia are. Quite often, standards in academia come from in a sort of bottom-up way. Rarely we have these organizations that are basically imposing a standard on everyone else. It's quite often a few even developers. That's actually how Nifty was coming around, that see the need for better exchange of information and less error-prone ways of transferring metadata. Quite often, the standards are developed with a specific project in mind. So, for example, which is very good. They are there to solve a particular problem for a particular project, which is good in a way that it is driven by a practical use case. But it's a little bit more limited because often those problems are constrained or limited by time, by grants, by a particular specific flavor of this problem in this particular specific project. And OpenFMRI, for example, a repository of imaging data I've been involved with, had the same thing. They needed to have some sort of formalized way of storing data, and they just came up with something for that particular project without involving broader community or negotiations or any consensus building. and that's perfectly fine. And this comes from the broader incentive structure in academia, where you basically are rewarded for solving particular specific problems rather than building consensus or broader collaboration. Standards academia also tend to be technically simple because, especially in biomedical imaging, quite often you have a mix of different levels of technical expertise, and that has to be accounted for, and therefore standards need to be basically simpler, so people whose expertise lies more in the biology could also benefit from using them and would not require, getting a CS degree to start building and working on top of a particular standard. And sometimes standards tend to be competitive in academia. So it is a bit unfortunate that the way scientists are rewarded is for making particular novel findings, and quite often that leads to competitiveness, and that leads to a particular group trying to do something before another group, and the reward only goes to the first person that does something. And that's why sometimes we do see some fights between standards, and we are seeing those fights being fueled by basically the incentive structure and how people are rewarded through grants. And then we also see the same benefits as with any standardization effort. When a particular standard gets widely adopted, there are great benefits, because suddenly we can combine different tools and different different software tools because they start talking with the same language. So an example of that is NIfty in neuroimaging research. This is an imaging file format which is very widely adopted right now, even despite some of its shortcomings. But because it's implemented in so many different neuroimaging research neuroimaging pieces of software, we are able to mix and match them and build optimal pipelines by picking and choosing algorithms from different sources. So this is great, and this is something that basically applies both in academia and in the industry. When we all start talking the same language, there are great benefits to come. Okay, so after this brief introduction, I would like to talk about a particular use case, and this is something that I'm a bit more knowledgeable about because it's a movement I've been spearheading. It's basically an attempt to standardize how we describe and annotate research human neuroimaging data. And I will try to make some broader points, because I fully understand that many of you are coming from different subfields of clinical research and not necessarily interested in the brain and imaging. But I feel that there are some take-home messages from this attempt that could be applied to different subfields, and maybe some of you will be engaged in standardization effort in different academic subfields in the future, and maybe some of this advice would be useful for you. So let me give you some introduction. First of all, and I think it's important for any project you start, is to think about your goals. So what are you actually trying to solve? Because it's so easy to go into the nitty-gritty details and start solving technical puzzles and forget about the particular big picture problem that you are actually tasked to solve. So we wanted to enable reuse of research neuroimaging data, and we wanted to make this applicable both to data shared within a lab and between labs. So the stress here is on reuse of data. So this is not just describing data for the sake of having a complete description of it. This is having in mind the actual application, the fact that someone generates a data set and someone else takes this data set and tries to extract knowledge from it. And this, again, this applies both within a lab and between labs. So even if you were to start adhering to standards in your lab alone, that gives you benefits because it's easier to collaborate within this lab with your peers, but it's also easier if you're on a higher position, for example, with a PI. It's easier to move one person from a project to another, or basically reuse some historical data acquired in your lab for a new project. We also wanted to enable automatic analysis of data sets. So when you have enough metadata and they are all formally described, that allows you to run analysis automatically. And you can start with small use cases when you just pre-process the data in an automatic way and you extract the metadata. And this is much less error prone, but the big picture vision is that we will be able to go from data to actual knowledge, to semantic knowledge in an automatic way if we have good standards for describing the data itself. And then finally, we'd like to have tools for checking consistency of data sets. And this is important in the context of data sharing, where you are receiving data from different sites and different groups, and you want to basically validate them relatively quickly in an automatic way. And we also need to think about the players. So you need to have in mind the people that you're building this for, and this will be very important later on when you decide what groups to actually contact and who are the key players for this thing to be successful. So we wanted this to be useful for lab PIs, and I said this is not just reducing errors in data handling, but also, very importantly, enable reuse of data within your own lab. And might sound a bit weird that I'm stressing out this within a lab use case, but with this project we had to fight this perceived notion that this is only useful if you are planning to share data publicly or widely, and this is not the case. It's a separate orthogonal issue, which I'm happy to talk to any of you at length later. But standardization helps whether you are willing to share data publicly or not. And then we have to talk about pipeline developers. Those are the people who build tools for processing data, so they know very well which pieces of metadata are necessary to be able to process the data. And then finally, databases and repositories. So those are both developers of the software, also curators and managers of these resources, because that enables automatic data submission, and they know very well what pieces of metadata they are asked for, and they have been dealing with a broad variety of data sets. Okay, and just to kind of drive home that message of reuse within your own lab, I usually, when talking to a new audience about the standard, I present this hypothetical situation of Professor Smith, who's up-and-coming researcher that is running her own lab, and she just came up with a new way of reusing old data that has been acquired in her lab a while ago. She remembers that this data was acquired by a particular PhD student who already graduated, and unfortunately the student, Mike, decided to become a business analyst or a data scientist, in other words, in California, and he's completely unreachable, and there's no way to get him involved in this project. And Professor Smith is trying to make sense out of her own data, the data that was acquired in her own lab, but is struggling, basically getting lost with this because she found eventually this external hard drive lying around somewhere, and it's a heap of incomplete DICOMs and Excel spreadsheets. So this is basically the use case we're trying to avoid even within the single lab space. So moving on, we also try to acknowledge what makes such endeavor successful. And many of these things that we learn on the job, but hopefully some of these will apply to future standardization projects. We really wanted to involve broad scientific community, and that basically means that you have to step outside of the bubble of your own lab. I mean, this is the essence of standardization. You need to find a common language. So if you only speak to people who are just next to you, that is much easier, but that doesn't enable this long-range communication. And here the concept of distance is much more abstract. So that means talking to different labs and talking to different researchers, even those that you would normally not actually interact with, and trying to figure out what are their needs, what are their experimental procedures, so on and so forth. And then sharing the credit of this work is very important. And that's one of the big changes or differences from building standards in industry and academia, is that in the industry, you usually have those panels where different companies would send their employees to participate and make things work and find the consensus. So basically have employees that are paid to work on a standard. In academia, this is a little bit different, and usually working towards standardization is not something that is rewarded by the same academic means. So that's why it's very important to share the credit of the work of a standard. So it means that you have to be truly collaborative and acknowledge all of the individuals that are involved in the standard in the way that is respected in academia. So I'm talking here about co-authorships of papers and other products. Then focusing on use cases is extremely important. So
Hello, everyone. This is Jack Van Horn. We're going to try and get Chris unmuted here in just a second. Hang on just one moment. Hang on just one second, folks. We're going to try and get Chris back here in a second.
okay, can you hear me now?
Yes, we can, Chris. Thanks.
Yeah, sorry for that demonitis, I guess. So I will assume that I got cut out at 9:33. Yeah, well, that's east. Well, anyway, the same slide. All right. So back on track. So focusing on the use cases, this is what I was talking about. it's basically having in mind the practical uses of the standard in the future. And that's why it's very important to get involved all these people that will be reusing the data or building tools to reuse the data involved in this. Then you have to make the process public and also document all of your calls for comments and different outreach operations. And that basically gives your effort much more validity. And then we try to follow this 80-20 rule, and this basically means that we are focusing on 80% of the most common cases instead of spending 80% of the time on the tail of 20% of the cases that are least common. And in other words, we basically don't want the strive for perfection to prevent us from delivering something that is good. And this is something that you have to remind yourself over and over again when dealing with these things, because quite often it's easy to be overwhelmed by the amount of details and amount of edge cases that you have to cover, and that can slow things down actually to a halt. So that's something that that is important. And finally, provide tools. So the standard itself, if you don't provide any tools, is just a long, boring document. But it was important to be able to help people adhere to this standard is to provide validators. And this is something that the World Wide Web Consortium excelled very in a great degree. They have validators for their markup standards, and that allows developers writing websites to check whether what they have written adheres to the standard. And I think that's very important to have for any standard. And then community. It's extremely important to basically build a community around your effort to make all the voices feel heard and have a healthy conversation about different things. You have to remember all these people will be donating their free time to this effort. So it's very important to make them feel appreciated as well. And building community is probably the hardest thing about coming up with standards in academia, but it's also the most important aspect. And on the topic of community, you might be asking, like, how do I get people involved? How do I get more people involved? And there are some practical, technical things that you can do to make that happen. For example, you should strive to ease the barrier to provide feedback. So in other words, you're gonna have some draft documents, you're gonna have some proposals, some ideas, and those ideas need to mature, and you need to have as much feedback from the community as possible to be able to turn this imperfect idea to something that is much more usable and captures perspectives outside of your own bubble. So practically here, we wanted to make it easy for people to communicate. We decided for an old school mailing list because a lot of experts in the field are very accustomed with this way of exchanging ideas. But we also went for an alternative to that we follow in parallel, which is an online Google document that is open for everyone and anyone to comment, even anonymously. And that's a great way, because you can just send a link to this document, and I can actually show you how this works right now. You can send a link to this document, and they can basically immediately not only have a look at the current working version of the standard, but they can also immediately say, they can immediately say what they think about it. So in other words, they can go here and they can start commenting on the format as it is. And as you can see, there are plenty of people that already left their comments as soon as this loads. And this is a quick way of getting feedback from the community that is outside of the mailing list, and also provides ways to give direct suggestions to the wording of particular definitions, for example. And then on the topic of credit, it's very important to list all of the contributors by name if they are willing to do so, and acknowledge all types of contributions. So there's going to be plenty of work with any standard, and some of it is documentation, some of it is building examples, some of it is building tools, and acknowledging all of this hard volunteer work is very important to make a thriving community. And also induces a feeling of shared ownership, and this is something very important because people should know that this is a collaborative product. This is something that that only came about because of a lot of dedication from many people. And then it's important to organize in-person meetings. Some things are just much better done when you meet face-to-face, and some discussions can go really badly only because they're done over email. And finally, be persistent, because most people will be too busy to help you out to begin with, and a lot of people will be skeptical in the beginning because no one knows if your idea in this particular standardization project you're working on actually is going to be picked up, is going to become a standard. Until it's widely adopted, it's just a proposal. So people don't know if they should dedicate time to it in the beginning. So lots of patience. So briefly, what is BIDS in more detail? I'm going to skim through this. It's a way of structuring, annotating, and organizing data. So in other words, it's not just a set of definitions of metadata fields, but it's also how particular files should be named and organized in a particular storage space. And this might sound a little bit backwards to some people, especially in the age of object stores. But we found that this is something that a lot of labs already do, and that particular approach was driven by the community need. Standards basically describes binary imaging data as well as demographic data for participants in scans, and for that we use TSV files, we use Nifty files previously mentioned for imaging data, and then JSON for other metadata, and all of these fields are well defined in the specification itself. I'm not going to go too much into the details of BIDS itself because I would like the messages here to be much more general. But I want to talk a little bit about the tools that are important for making BIDS happen. And obviously there will be APIs, and there are APIs being built for BIDS that allow you to query those data sets programmatically in various languages such as Python or MATLAB, and that's important, the sort of tooling that makes adoption easier. That is very important. But at the same time, the standard itself has to be easy enough for those tools to be built quickly and easily. In other words, you cannot build all of these APIs for all of the languages yourself. So you should not rely on the fact that everyone interacting with the data described using your standard has to use your tool. And then converters, there's a lot of idiosyncrasies in the data that needs to be converted to the standard, and that's why converters are extremely important. And finally, validators. And I cannot stress it enough, the role of the BIDS validator is very important. It basically allows you, and I will attempt to demonstrate this right now, it allows you to, on your own machine, point to a folder on your hard drive with the data set, and it performs validation of this data set client side. There's no data share. This is all in the browser using JavaScript, but without any data transfer, and it shows you what sort of errors, what sort of missing metadata pieces there are in your data set, and that takes you from reading a boring specification to actually adhering to the standard much quicker. And then we have a process for creating extensions. That's another important aspect of standardization, is that this is always a live document, so always will be extensions. And it follows a standard procedure that is similar in IEEE and World Wide Web Consortium, where there are drafts, there are experts involved, there are calls for public comments, and then we create examples and we extend the validator. And we strive for consensus before we merge it, and we are very big on backwards compatibility, especially because there are so many tools building on it right now. And many of these extensions are being driven by certain individuals that can kind of pick up the role of chairs of the subcommittees, and I just want to list some of them here. Cyril Pernay, Melanie Gantz, and Dora Hermes, as well as Tarek Koni were working on some of these extensions, and there are many others not listed here. And some of these extensions actually lead to independent academic products. So, for example, extending bits to MEG has been described as a paper that is currently under review, and this is work driven by Guillaume Niso from McGill. But to sort of wrap it up, because I feel that the time is sort of running out, I want to talk a little bit about the use cases enabled by bits, because standardization is all great, just have a language to talk to each other, but what cool new things can we actually do when we have this standardization? And one of the things that we started doing very early on is trying to build containerized applications for doing data processing that can take a standardized bits data set. So this is a concept kind of similar to what you have on your phone. When you install an app on your phone, you are never worried about dependencies or other software that this app relies on. So you married this concept, which is called software containers, with taking standardized inputs as taking standardized data set as inputs. So that allows us to create a set of different processing applications that require minimal metadata inputs and allow you to very quickly test in a also very reproducible way different analysis and different pipelines on your data set, as long as it is in a standard way. And the other thing that we also did, marrying different aspects of these concepts, is that we've created a free online platform for sharing and analysis of neuroimaging data. And this platform builds on many of the components that already spoke about. But the important take-home message here is that the components, such as the validator, such as the bits apps, are all independent, and they are basically building blocks that other people can use to incorporate this into their own systems and services and website and tools. And I think that's an important thing to emulate, because that, again, this is not about a single lab. This is not about a particular set of individuals. You're trying to build an ecosystem, and to do this right, you have to make your components and tools reusable. All right, so going back to Open Neuro, so this is a web platform that uses bits apps and uses bits to make data sharing, data analysis easier. So basically, it allows users to upload data sets to this website, openneuro.org. And then again, the validator, exactly the same code base I showed you before, is being run before you upload the data, so you know if there are any errors that you have to correct before actually committing to like a long data transfer process. And then it allows you to to basically, when you upload your data set and you create a snapshot of it, it allows you to choose from a library of different BIDS apps, or basically containerized data processing pipelines, and you can schedule a job running those BIDS apps in the cloud that is managed by this website. And this is basically how you can schedule the job and select different subjects. And when you press submit, you're going to get an email after the job is finished, and you can go and explore results of such analysis. And I can show you, before we move on, a little bit how such analysis actually looks like. So here we are, we're on OpenNeuro, and I uploaded my own brain because vanity, I guess. No, it's because I can actually clearly share my own brain. That was an older project, and basically, as you can see, I can go to different data sets and look at different parts of the website, and we have both public and private data sets, but let me just go to my very own data, and after a moment I can show you actually the jobs as they finished. For some reason the internet is acting up today a little bit, and I'm not quite sure. Oh, okay, there we go. So I run a set of different apps on this particular data set. And for example, here, this is Ant's cortical thickness app, which finished and succeeded. I can go through the logs, and I can also look or download through the results. And for example, one of the outputs of this particular pipeline is this image of the brain segmentation. And when it loads, you're basically going to see how well ANTS, which is a particular piece of software for doing structural and functional brain co-registration and segmentation, worked out on this data set. So yes, so this is how this works. And just to wrap up, I would like to thank many or all of the contributors to BIDS and the BIDS ecosystem. As you can see, it's a long and growing long and growing list of names and institutions that contributed in different ways to this effort. And we hope that this list is going to grow even more, and we're going to make even better standards. I also compiled a list of resources that you can have a look if you want to learn a little bit more about the things that I talked about today, and that includes the IEEE and W3C processes, as well as history of DICOM, and some of the BID stuff that I talked about. And I guess this is all from me, and I believe that we have some time to take questions.
Chris, thank you so much for that really great overview of the need for standards and why we kind of need to have them from a practical standpoint, and some of the sociological issues as well as some of these providing some of these resources for us. One question that I guess I have is, very often you'll see where there's a new standard that's being kind of announced, and there's some group someplace that says, oh, we've decided that there needs to be a standard, and we've anointed ourselves as the standard creators, and we're going to make the standard, and you'll all love it, it'll be great, you should want it. As an end user, how can one be comfortable with this, almost this barrage of standards development, and knowing which one is the most trustworthy, or is it needed, and do I kind of make the leap to change the way I do my own data standardization, or rather what form I put my data in? How do I know when's the time to do this, and how do I know to trust the people who are saying that, oh, we've developed this standard and it's great, you should adopt it? How do I know?
Well, such an easy question to start with. Yeah, of course, I'm kidding. It's an incredibly hard problem, So the telltale signs is adoption, but that's a chicken and egg game, yes, because someone has to be the first one to do it.
Right.
So the other thing that you can go with is seeing which individuals or which organizations are actually involved in this process, and if there is a process, if there actually has been like a broad communication about how this has been developed. But at the end of the day, everyone adopting something new is taking a risk, because it might be good or might not be. So there are ways to minimize that risk. If you are it's probably good to commit with a smaller project, maybe delegate it for a new array, collecting a new data set and gather some information this way, rather than committing a whole consortium to it to begin with. But yes, this is the struggle, and that's why, especially in the early days of BIDS, we struggled to get people involved, because they were hesitant, because they didn't know if this thing's going to pick up or not.
Well, I guess everybody has, sort of a finite energy that they can devote to things, and if it looks like they have to do a whole-scale, a transformation of the way they organize their data or store it or what have you, that, I don't know, for some people that might be a horrifying thought. I mean, one thing they might be thinking is that, well, wait a minute, here's some new standard. Is this based on something I already know? So, for example, one of our listeners is asking, is the data set description based on the HCLS W3C data set description? And somebody may say, oh, I'm familiar with that, so okay, this makes sense to me, and that might lower their barrier. On the other hand, if it's, I'm not speaking about BIDS in particular, but if people weren't familiar with that, they may say, well, wait a minute, why would I go and do this? Because it seems to be unattached to anything else that I might be familiar with. Is there any sort of sociological barrier there?
Yeah, totally. And I think that what is important here is that they totally agree that those links, that building on existing solutions is very important. But it's also important to acknowledge that different communities will sort of respect and acknowledge, or actually be familiar with, different existing solutions. So for example, there are some unwritten practices in the way that people organize their data in academic labs that they are familiar with. There's the imaging data storage format called Nifty that a lot of people are familiar with. And there are some excellent standardization approaches of data in the industry that academics might not be familiar with. So it's not only building on things that are already there, but also acknowledging what your community is familiar with and what they're gonna basically take advantage of.
Mm-hmm. And how big of a role do, say, journals play in this? And while there's a lot of interesting sociology regarding that, which we don't need to get into, about what for-profit or open science or like bioRxiv or what have you, but journals play an important role here in that they're publishing the research. Do they have any sort of, I don't know what your experience has been, have they had any sort of buy-in to the acceptance of standards in support of the literature that they publish, so that the data that's contained in them is more easily reproducible?
Yes, so in a way it was rather indirect, and there were two aspects where journals actually contributed to this. One was when we were trying to publish the standard itself as a paper. They've pushed that in the right direction to be more transparent about all the things that we did to reach out to the community, and I think that was very important, and sort of emphasized our what we knew already, but it's better to make this all transparent. And the other aspect how journals are involved in this is there's this new breed of journals that publish data. So those are data journals, in other words. And I'm talking about scientific data here, data in brief. Frontiers is doing that, neuroinformatics is doing that. There are specialized data journals for social sciences and psychology as well. And those journals, since they publish data or data descriptors, they care a lot about the consistency and the reusability of those data sets. And they usually sort of offload the burden of data over indirect. As for example, there are a few journals that would recommend repositories that adhere to standards, but they wouldn't recommend standards themselves. So this is how journals basically play a role in this.
Right. Well, we're at the top of the hour now, and I'd like to thank you, Chris, for providing this great overview of data description standards for biomedicine. Perfect addition to our collection of webinars on in the guide to the fundamentals of data science. I'd like to thank everybody for joining in. Once again, thanking Chris, and do look forward to future of our Guide to the Fundamentals of Data Science webinars, and watch your email for further announcements about those. Wonderful. Thank you very much. Everybody have a wonderful day and a great weekend. Thank you.
Thank you for having me.